And now for the last speaker, we before the pause. And sorry, I also changing the order. So the last speaker for this first part will be Josh Mitteldorf. Welcome, Josh, and please, if you can, share the screen. And for this, I have also to stop the screen, or if somebody can stop the screen of.
I don't have anything to share at the moment.
Harold.
Yeah, but
I'll have a couple.
You are only speaking. Okay,
You
that's
can hear
great.
me?
Go ahead, Josh. Yes.
Thanks for the opportunity to speak here. I'm in distinguished company, and I really appreciate it. I'm a theoretician. I wish I had the kind of data that some of you have presented. Is really impressive. So I'm going to speak from a much more abstract perspective. Think about the last time you were sitting on a plane. You're leaving the gate. Hello?
Sorry, I didn't recognize you. I think you look younger, suspiciously younger.
I've been taking elixir on the side. I didn't tell you about that. So how many of us have had the experience sitting on the plane on the tarmac, getting ready to leave, and the plane stops for a long time, and over the PA system, the pilot says, there's a bad valve in the hydraulic system in the left aileron, and we're waiting for them to locate the part. I'm sure you've had that experience. How many of you have had the experience, but he comes back on a minute later, no, never mind. We found a spare capacitor on the radar system, and it just happens to have the same size and shape as the valve that we needed, so we'll just use that instead. Flight attendants prepare for takeoff. No, you haven't had that experience. It's because airplanes, like everything else manufactured, has parts that are each optimized for one function only, and the parts are assembled in a particular order that's logical, and the machine works in one particular way because each part works in one particular way. When evolution was designing humans, that's not the mode that they used. Your bones have a function of supporting the body's frame, but they also store calcium and they manufacture blood cells. And your liver has God knows how many different functions, hundreds of different enzymes manufactured in the liver. The point is that biology doesn't work with one chemical, one function. There are many functions performed by many chemicals. They're all overlapping in this incredible net, and it's a challenge to unravel it all. Historically, the term for gene was coined in 1905 by Wilhelm Johansen, when the pioneering work of Gregor Mendel half a century earlier was just being rediscovered, and DNA was not yet a thing. Biologists were hopeful there would be one separate gene for each trait. And even though they were flying blind, so to speak, they were doing inheritance experiments with no knowledge of the molecular mechanisms of inheritance. Still, they figured out very early that the body doesn't work the way a human designer would have designed it. The word epistasis was coined in 1909 by Gregory Bateson, and it meant gene interactions. Several genes have to combine to create one phenotype. The very next year, Ludwig Plot coined the term Plyotropy, and that's the converse. A single gene has multiple effects. At the time, these words were coined because they thought, these are the exceptions, the rule is one gene, one trait. But soon it was learned that that's just not the case. The body is not engineered the way we would engineer a machine. Every molecule has multiple functions, and every function is regulated by multiple molecules, actually multiple pathways. Before we curse the body for being organized in this way, this makes it inscrutable to us, consider the benefit is that we're not waiting on the tarmac every time there's a single part of our body that doesn't work. The body is wonderfully, amazingly, robustly homeostatic. There are far more so than any human engineered machine that's designed for maximum fault tolerance. So many of you know me as an advocate for the perspective of programmed aging, which means there's a clock in the body that controls what age, the age of the phenotype, and it's controlled systemically. I've come to think that these changes are epigenetic, that epigenetic changes in gene expression are probably the primary driver of aging. And there was a time just a few years ago, I was hopeful that this means there's a biological clock coded into the metabolism. We could find that clock and set it back. There was a time I even thought perhaps the clock was leukocyte telomere length. And then there was a, see if I can do this. Can you see my screen? No.
Yes. We can
good.
see your screen.
It works.
Yes.
There was a time when I thought that leukocyte telomere length was the key. And then I saw this slide from a study by Rode et al. 2015, Danish people plotting telomere length versus age. And of course, there's a correlation. There's a slope downward, but it's not nearly tight enough to think that telomere length is the aging clock, or even a very large part of it. So I now believe that the age stated is encoded in a clock, but that clock isn't simple and it isn't localized. Like everything else in biology, it's spread out over many systems with many different functions. This view is still optimistic in the sense that I believe we don't have to repair all the damage that the body suffers. Most of it can be repaired by the body itself if we just restore a young signaling environment. But less optimistic in the sense that it will be more complicated to understand and ultimately to manipulate the body's clock or clocks. You know, I'm a fan of Harold Kachur's work. He just spoke. And from what he claims, he has a way to set all the body's primary clocks back at once. Suspending disbelief, I want this to be true. I expect and hope that it will turn out to be a big advance in not only anti-aging, but de-aging, rejuvenation. And I'm impatient for Harold to disclose the methods so that they can be replicated in other laboratories around the world. So let's see, where are we? So if there's one point that I want to leave you with from this whole presentation, it's that we've been testing interventions mostly one at a time in the spirit of reductionist science, which is a venerable spirit. And we know that that's not going to work. The interactions are not a secondary effect that we can worry about later. The interactions among different interventions are as strong as the interventions themselves. And of course, most of the interactions that we're talking about are redundancy. So this is from a few years ago. At the time, the 15 interventions that I thought showed the most promise. And how much increase in lifespan they were able to induce. from these 15, if you add them all up, you get 172% increase in lifespan. And I don't think any of us believes that we could just do all these things and make a mouse live 172% longer, let alone a human. Many of these interventions act on just a few pathways. In particular, there's acarbose, caloric restriction, there's metformin that all act on the insulin pathway. And we know that the insulin pathway gets saturated. And furthermore, the insulin pathway is probably more effective in short-lived animals than in long-lived animals. Some of these others act on inflammation pathways. And again, we know the inflammation pathway is powerful, but it will be saturated at a certain point when inflammation is back to youthful levels, and adding more anti-inflammatories is not going to make is not going to increase lifespan further. So if we wanted to test combinations of these, it may be daunting to think about how quickly the number of combinations multiply. With just these 15 treatments, there are 105 pairs, combinations of 2, or 455 combinations of 3. How are we going to test them all? It seems like an enormous burden on laboratory time. But the saving grace is that we don't need to characterize each of these with a full complement of 30 or 40 mice, measuring the survival curves. We don't care about the details. We just want to identify combinations that stand out head and shoulders above all the rest, giving extraordinary benefits. And these should not be so hard to identify. If there are mice that are living for 4 years instead of 2.5, we don't need 30 mice to find that out. We should be able to observe the reliability with just 3 mice per combination. So 4 years ago, I was promoting a protocol for screening combinations of treatments in rodents. I proposed 3 mice for each of the 455 triplets for a total of 1365 mice. In computer simulations, I showed that if there was a combination that offered a 50% life extension, that combination would be identified with just 3 mice with a reliability of 80%. No one has yet done that study. I would like to see it done, but maybe we can do even better. You know about the TRIM study, published 1.5 years ago, using a 5-way combination of growth hormone, DHEA, zinc, metformin, and vitamin D. And they successfully, at least in a pilot study, successfully reversed immune aging and found evidence of reversing epigenetic age as well. Just this last year, I worked with Dr. Cara Fitzgerald, who made some inspired guesses about combinations of diet and lifestyle interventions that ought theoretically to promote younger methylation patterns. In a pilot study of 18 men, her very brief 8-week intervention already showed preliminary signs of success in reversing methyl age, especially for people with a particular MTHFR SNP, which is common. It was half of her subjects. 2 years ago, I proposed a study in humans using methylation clocks rather than survival curves. I thought at that time that the methylation clocks were accurate enough that we don't need to wait for humans to die and measure their mortality curves. We should be able to tell within 2 years whether any combination is working well enough to slow aging by 25%. So my idea was to harness a natural experiment. There are hundreds of thousands of people around the world who are aggressively pursuing anti-aging on their own. Each is using some individual strategy or combination of strategies, pills, exercise, diet, etc. And the Data Beta project is what it's called. The Data Beta plan is to recruit 5,000 of these people, early adopters, biohackers, and get a diverse sample of the things they're doing, offer an extensive questionnaire about everything that they're doing, and then we'll test them with methylation clocks at the beginning and the end of a 2-year period. We anticipate a lot of these things won't work. People will just be 2 years older at the end of 2 years or close to that. But we'll look at the tail end of the distribution, maybe the 5% of people who are aging the slowest. We'll look for the commonalities among those 5. Are they just random samples of everybody else? Or are there some combination of 3 or 4 or 5 things that all of these 5% of people are doing? And then we'd have a combination that we can recommend for further testing, do specific tests on that particular combination of interventions and test it in more detail. So the idea is a screening rather than a broad screening, rather than trying to study one intervention at a time or a combination of interventions in more detail. I wanted to show you the website for DataBeta, which is databeta.io. It's database for epigenetic evaluation of treatments for aging. Let's see if I can get this up. There it is. This is the DataBeta website. Thanks to a generous contribution from Didier, we are starting up. We have university collaboration with McGill University. We've spent a long time going through their IRB process, which is very conservative, convincing them that we have a viable plan, even though it's a very unconventional program. And we hope to be recruiting people for this study starting in the next month or two, by this spring. And lastly, I want to suggest an idea which I haven't put forth before today, but combine the two. Before I was talking about rodents using lifespan, and now we're talking about humans using methylation. Even more efficient is to screen a great number of interventions using rodents and the recently developed Horvath clock, which is supposed to be valid for 128 different mammals. So we could screen interventions that we hope might rejuvenate these animals and use a great number of combinations over a very short time, cutting costs by making the program just a few weeks long, and see whether any of these interventions are working. Is there anything that, for example, can duplicate the extraordinary success that Dr. Katcher reports? I would love to see that study done, and I'm done and ready for questions.
Thank you, Josh, for your presentation, for your speech. We are already almost 10 minutes ahead of time, so I propose that the questions and the answer will be in the chat. And now we will have a pause for precisely 10 minutes, 600 seconds, not one more, not one less. So you have the time for one coffee if you want, but except Josh, who has no time because he has to answer the questions online and also